In this video, I'm going to show you a basic result from Fourier analysis called Pisier's inequality. I really like this result because it involves a lot of very clever ideas that I think are widely applicable to many other problems. Okay, and I don't think it's as well known as it should be. Now, my goal is to just explain the high-level ideas and the key interesting ideas involved in proving this inequality. So I'm going to go fast. I'm going to skip a lot of details that I think you can figure out for yourself. So if at any point something I say is not clear or there is a gap, then you should pause the video and think about how to fill in the gap for yourself. So let me start by reviewing some basic concepts from Fourier analysis. For every function f that maps the cube into the reals, Fourier analysis says that the function f can be viewed as a polynomial like this, where these constants here are called the Fourier coefficients of f. Now, if the function maps not into the real numbers but into a higher dimensional space, okay, like this, then the same identity holds, except now the Fourier coefficients are vectors. Now, a basic identity for analysis is Parseval's identity, which says that the 2 norm of f, okay, which is this expression, can be expressed in terms of the Fourier coefficients like this. It looks like the Euclidean norm of all the Fourier coefficients. Okay, and that's really a basic identity. And one consequence of that identity is that if you just look at the linear part of f, okay, take f and project it to its linear part, meaning drop all the other Fourier coefficients and just retain the ones that are at level 1, then the 2 norm of the linear part is at most the 2 norm of the entire function. Right? When you restrict your attention to when you project f down to a subset of the Fourier coefficients, the 2 norm can only go down. This is a feature of the 2 norm. And Pisier's inequality is about understanding what happens when you have norms that are not the 2 norm. You know, what happens when you have other kinds of norms? So now here I've just stated the results that I discussed on the last page. But given an arbitrary norm on R to the m, you can define a norm on f like this. Okay, it has the same expression as the 2 norm, except I replaced the 2 norm here by some arbitrary norm. And then what Pisier's inequality says is the norm of the linear part of f is bounded by order log m times the norm of f. So that's the result that we're going to prove. Now, this result is tight. There are examples of norms where you really need the factor of order log n. Okay, you cannot do better. And this is a really beautiful inequality. I learned about it when I was learning a basic result from convex geometry called the MM polar estimate. I made a video about the MM polar estimate, so if you haven't seen that, you should watch that video as well. That'll show you a nice application of Pisier's inequality. So let me try to show what this inequality establishes, or give an example of what it establishes in pictures. So suppose you have some arbitrary norm, and let's say this is the unit ball of that norm, and this is the ball of radius order log m. Then what Pisier's inequality says is that if you have a function that maps all of the points of the cube inside the unit ball, it cannot be that when you project the function to the linear part, then all of the points get mapped outside the ball of radius order log n. Okay. So it cannot be that the linear part maps the points very far away, according to this norm. So that's what the result says. Now, I'm gonna, the proof of Pisier's inequality involves a lot of clever ideas, so I'm going to now explain the proof. We're going to work up to it by making a couple of false starts that give some result in this direction, and involve some key ideas, and then eventually we'll put all these ideas together to get the real bound. Okay. So the first false start is to use John's theorem. Okay. John's theorem is another basic result from convex geometry. I've made another video about John's theorem, and you can watch it if you haven't heard of John's theorem before. But what John's theorem says is that an arbitrary norm can be approximated by the 2 norm. Okay. Given an arbitrary norm like this, there's always a linear transformation J, an invertible linear transformation, such that the norm can be approximated by the 2 norm applied to J of the input in this sense. Okay. The approximation is off at most by a factor of square root m. And John's theorem is also tight. Okay. John's theorem is tight. But this already gives a way to try and prove something like Pisier's inequality, which is that we'll just use this approximation and try to move from the given norm to the 2 norm. So let's try and do that. So we want to bound the norm of the linear part of f. Now by John's theorem, well, what is this? So this is the expected value over x of the norm of f ln of x squared to the 1/2. By John's theorem, I can upper bound this by square root m times j of the linear part of x. And now I've moved to the 2 norm. But for the 2 norm, I know that the linear part can only be less than or equal to the 2 norm of the linear part can be less than or is at most the 2 norm of the entire function. So this is at most the square root of m expectation over x of j of f x. And then applying the other, so far we've used this inequality in John's theorem, but now we'll use this one. And that gives us that this is at most square root of m of the expected value of x of norm of fx squared. Okay, so John's theorem says that by passing to the 2 norm, we can show that you get a bound of square root m times the norm of f here, and this is off by it's exponentially worse than the correct bound proved by Pisier's inequality. Okay, but still John's theorem says something. So that's one idea to keep in mind, and eventually we will use John's theorem in combination with some other ideas. The next idea that's useful is convolution. That's because projection to a subset of the Fourier coefficients can be expressed algebraically using convolution. So let me review what convolution means. Suppose you're given 2 points x and y in the Boolean cube, then let's define their coordinate-wise product using this symbol. Okay. This is the coordinate-wise product. And now if you have a function a mapping the cube to the real numbers and another function f mapping the cube to the to vectors, then the convolution of a and f is this expression. It's expected value of y of a of y times f of the coordinate-wise product of x and y. And a basic fact about convolution is that convolution has a very nice behavior in Fourier space. It corresponds to multiplying the Fourier coefficients together. Okay. And the way the setup is here, let me just remind you that these Fourier coefficients, they are numbers, and these Fourier coefficients, they are vectors. Okay. But this is the product of a number with a vector. And that's very powerful because now if I want to express the linear part of f, that's the same as a convolution of f with this function, the function which is just the sum of the variables, because this function has Fourier coefficients that are 1 exactly when the coefficients are the sets are of size 1 and they're 0 otherwise. Okay, so this convolution by this identity is the same as a linear part of f. So now let's try and use this to bound the norm of the linear part of f. Let's see how to do it. So suppose we want to bound the norm of the linear part of f. That's the same as the norm of the convolution of L with f, and let's write it out. That's equal to the expected value over x of the norm, the expected value of y, of L of y times f of the coordinate y's product with y squared to the 1/2. Alright, now I'm going to use the triangle inequality of the norm to bound this. This is at most the expected value over x of expectation of y This is by the triangle inequality of the norm. Okay, great. So what we have written in here looks like an inner product. It's an inner product of two vectors, and we're squaring the inner product. So I'm going to use the Cauchy-Schwarz inequality. And using that inequality, what I'll get is that this can be expressed as expectation over y of L of y times the expectation over y of the magnitude of L of y norm of fx product y squared. Okay, so if it's not clear how I use the Cauchy-Schwarz inequality, think of breaking up this term into square root of the magnitude of L times square root of the magnitude of L. Okay, and then apply the Cauchy-Schwarz inequality. All right, so now we've reached a good state, because you see this number doesn't depend on x at all, so I can just take it out. Okay, so this is at most the expectation over y. And what's written here in the second term, the coordinate-wise product of x and y is independent. This is independent of that. Okay. So this is equal. Okay. Basically, these two terms are independent, and this term, the second term here, just contributes to the norm of f. All right, so this is great. Now I got a bound in terms of the norm of f. And what is this expectation? Well, if you take the sum of a random point in the cube, the sum of the coordinates, then typically the value you'll get is square root n. Right? The typical magnitude is square root n. So what's written here is more or less bounded by order square root n times the norm of f. So again, we got a bound in terms of the norm of f, but it's not quite the right bound. The factor we got is order square root n. And if n is much is polynomial related to m, which is often a typical application, it's what you need for the mm polar estimate, then this bound is much weaker. Okay. To prove our final bound, we'll use a linear proxy. This is a function p that is very similar to the function L that we just used, except that it has small L1 norm. Okay, so P has the property that all of the level 1 Fourier coefficients are 1, just like in L. And all other Fourier coefficients are tiny. Okay, for a parameter d, they will be exponentially small in d. And yet the L1 norm of P is linear in d. So let me first start by showing how this linear proxy can be used combined with the ideas we've already seen to prove Pisier's inequality. So we want to bound the norm of the linear part of f, which as before I can express as the convolution of L with f. And this I can write now as the norm of L minus p convolved with f minus p convolved with f. And now I can write use the triangle inequality to bound this by L minus p convolved with f plus the norm of p convolved with f. And I'm going to bound both terms separately. To bound the first term, I'll use John's theorem. So John's theorem says that this quantity is at most, now I can move to the 2 norm, I get a factor of square root m. It's the 2 norm of L minus p convolved with f, convolved with j times f for some linear function j. And now let's look at the properties of p. Because of the way the guarantee of p, on the Fourier coefficients, L minus p, every Fourier coefficient of L minus p is extremely small. It's bounded by this number. And that means the convolution in Fourier space, every Fourier coefficient of j times f is being reduced in magnitude by this exponentially small number. So I can bound this quantity by square root m times d times 2 to the minus d times the 2 norm of jf. Which again, by John's theorem, by the choice of j, is bounded by square root m times d times 2 to the minus d times the norm of f. So in this way, if we choose d to be roughly order log m, then this bound is good enough to make, this quantity can be made very small. Now to bound the second term, we'll use the calculation that we just did. The norm of the convolution of p with f can be bounded by the expectation of the magnitude of p of x times the norm of f. This is exactly the same calculation as we just did with L, when we used L instead of P. And now we appeal to the fact that L1 norm of P is small, so this gives a bound of order D times the norm of F. So you see that if we set D to be about order log M, then this proves Pisier's inequality. So the heart of the matter is constructing a linear proxy with these properties. And that's what I'll do next. To construct the linear proxy, I'm going to use Chebyshev polynomials to build a filter. Now, I've made another video discussing Chebyshev polynomials, so if you're not very familiar with them, you can watch that video to learn something about their structure. But what we're going to do ultimately is make a distribution on numbers theta and a function phi of theta with the property that for k in between 0 and d, the inner product of phi with cosine to the k theta is 1 if k is equal to 1 and 0 otherwise. Okay, so this phi picks out sort of the linear powers of cosine theta. Moreover, the L1 norm of this phi is bounded by order d. Okay. In fact, it will be exactly equal to d in the construction that I'll show you. And let me now explain how to use this filter to construct the linear proxy. And this is a clever idea. You can write p of x, so here's the construction for p of x, is 2 times the expectation over theta of phi of theta times 1 plus x1 cosine theta divided by 2 times 1 plus x2 cosine theta divided by 2, and so on. There are n terms in this product here. Now, if you think about it, the properties of the filter, these properties imply that if you look at the Fourier coefficients of p and look at the first d levels, then only level 1 survives. All other levels are made 0 because the filter annihilates any power of cosine theta that's not 1 among the first d powers. And the level 1 Fourier coefficients are exactly 1 by construction. Okay. For the levels that are higher than d, what ends up happening? Well, if you look at expected value over theta of phi of theta times cosine of, say, d plus 1 theta, that's bounded by the expectation over theta. By the triangle inequality, it's bounded by the norm of the average magnitude of phi theta, which we're promised is equal to d. Okay. And that means if you look at the Fourier coefficients here that correspond to monomials of degree larger than d, then all such monomials have 2 to the minus d minus 1 factor coming from these terms. There's a factor of 2 here, and then a factor of d here. And the product of all those numbers is exactly what's written here. Okay. And the higher monomials are even smaller. They're even smaller in magnitude. So that establishes these two facts. To bound the L1 norm of p, let's look at it. The expected value over x of the magnitude of p of x. Well, by the triangle inequality, this is at most the expected value over x and theta of the magnitude of phi of theta times the magnitude of these n terms in the product, these n terms. But all of these terms are positive, okay? Because x1 is either plus 1 or minus 1, cosine theta has magnitude at most 1. So these terms are all positive. And moreover, after you fixed theta, the expected value of this product is 1. Because it's the product of n independent numbers, each of whose expectation is 1. So the upshot is that this is equal to the expectation over theta of the magnitude of phi theta, which is equal to, I left out a 2, so there's a 2 here, which gives me 2d. Okay. So that's how the filter implies the proxy. Now all that's left is for me to prove that such a filter exists. Okay. To make the filter, I'm going to use the properties of Chebyshev polynomials extensively. Okay, so here's the filter that we want to construct. And here's the formula for the function phi that we'll use. Okay, it looks a bit complicated, but I'm going to explain where this formula comes from. Our distribution on theta is going to be a uniformly random angle among the 2D equally spaced angles. Okay, so let theta be either 0 or pi over d or 2 pi over d and so on. There are 2D options for theta. Now, to explain the intuition for the construction, a basic observation is that the expectation over theta of e to the I k theta is 1 if k is equal to 0 modulo 2d for this choice of theta, and 0 otherwise. Okay. This is basically, comes from writing this expectation as a geometric sum. That's one way to check it. And a consequence of that is that if you take the expectation, the inner product of cosine d theta with a polynomial in cosine k theta, or where k is less than d, you'll get 0. And if k is exactly equal to d, you'll get 2 to the minus d. Okay, one way to see this is to use the identity, cosine theta is equal to e to the I theta plus e to the minus I theta over 2. And so this expectation that we're trying to compute can be expressed as e to the I d theta plus e to the minus I d theta divided by 2 times e to the I theta plus e to the minus I theta divided by 2 to the power k. And you see that if k is small, then you never get something with phase 0 in this expression. And if k is equal to d, then you get exactly 2 terms in this expansion with phase 0. Okay, and you can see what they contribute. So that's a nice identity. It means that cosine d theta basically gets rid of all lower powers in cosine k theta. And eventually what we're going to show here is this, in many of the cases that we analyze, this will be a low degree polynomial in cosine k theta. The next couple of observations that are useful here have to do with the structure of the Chebyshev polynomials. So the Chebyshev polynomial is cosine d theta expressed as a polynomial in cosine theta. And I want to make a few claims about these polynomials. The first claim is that when you write cosine d theta as a polynomial in cosine theta, the degree term, d term, has coefficient exactly 2d. Okay. That's the first claim, and that's true whether d is even or odd. The next claim is that if d is even, all the powers of cosine d theta here, cosine k theta, where k is odd, do not occur. Okay. So all the odd coefficients are 0. And when d is odd, all the even coefficients are 0. That's the second claim. And both of these claims follow from, again, writing down e to the I d theta plus e to the minus I d theta over 2, and comparing that to whatever you have on the right-hand side. Okay. When you write down the expansion for cosine d theta here, for example, you get e to the I theta plus e to the minus I theta divided by 2 to the power d, and you see that this is the only term that contributes phases as large as this in this identity, and that narrows down the coefficient that needs to be here. Okay. And similarly, to see that the even terms don't show up, well, if you have an even power here, then the phases that come out of this are all going to be even. Okay. And that shows that they cannot contribute. And the final set of claims I want to establish is, I want to say that when d is even, the constant term here is exactly minus 1 to the d over 2. And that just follows from this identity, right? Because this constant term is obtained by plugging theta equals pi over 2 on the right hand side. And when you look at the left side, you get cosine of d pi over 2, which is equal to minus 1 to the power d over 2. Okay. And similarly, to compute the coefficient of cosine theta here when d is odd, take the derivative of both sides and then plug in 0, right? So if we've written here cosine d theta is equal to t of cosine theta, and that means that d sine d theta, or negative d sine d theta, is equal to the derivative of cosine theta times sine theta minus. And now if I plug in theta equals pi over 2 here, I will get... Actually, the claim that I want to make is that this last coefficient here is plus or minus d. Its magnitude is d. And I can obtain that by plugging in cosine theta equals pi over 2 in this expression. Okay. All right. So good. So now we have all of these facts, and let's try to use it to reason about what's going on here. Well, there's one last identity I need, which is that sine theta sine d theta is equal to cosine of d plus 1 theta minus cosine of d minus 1 theta minus or divided by 2. Okay, and that means in particular that this is a polynomial in cosine theta. It's a polynomial of degree d plus 1. And therefore, this expression here, it's been set up to exactly delete from that polynomial the constant term and then divide by cosine squared theta. Okay, so this expression, as a result, this is a polynomial in cosine theta of degree d minus 1. It's a polynomial of degree d minus 1. And that means that when k is equal to 0 here, when k is equal to 0, what we have here is the expectation of cosine d theta times a polynomial in cosine theta of degree d minus 1, and it must be 0 by this property. When k equals 1, what we have here is a polynomial of degree exactly d in cosine theta, and so the inner product is determined by the leading coefficient, but the leading coefficient just so happens to be exactly 2 to the d, and so this property gives that establishes the case, establishes the identity for k equals 1. When k is larger than 1, then I claim that again you get 0, and that's because when k is larger than 1, what you have here looks like the expectation over theta of phi of theta, but this expression is equal I just drop this constant term, and I can do that because the difference between this polynomial in cosine theta and this polynomial in cosine theta is a polynomial of degree at most d minus 1 in cosine theta. So all such terms in the difference vanish. So these two quantities are equal when k is at least 2. But sine d theta on our choice of theta, sine d theta is always 0. So this is just 0. Okay, so now I've established this feature of the filter, it only remains to bound the L1 norm, which I will do next. To bound the L1 norm, notice that the sign of phi theta is the same as if, this part always has the same sign. Okay, because sine theta times sine d theta has magnitude at most 1. And then you're either adding 1 or subtracting 1. So the sign of this part is always the same. The sign of this part is always the same. And cosine d theta on input theta from the set is either plus 1 or minus 1. And so the upshot is that the magnitude of phi theta can be expressed as the absolute value of the product of phi theta with cosine d theta. Because all the terms that show up in here have the same magnitude as phi of theta, and they all have the same sign. They all have exactly the same sign. Okay, so we have this identity, and now you see that because phi is a filter, we've already proved this part. What we're going to get here is the linear coefficient of cosine theta, which I explained has magnitude at most d. So this is equal to, has magnitude exactly d. So this is equal to d. All right, so I used a lot of properties of Chebyshev polynomials in this proof, and I hope you enjoyed it.